Thanks very much for giving me the opportunity to talk about some long-term multi-factor global change experiments that we've been working on in temperate grasslands. And I want to start by acknowledging my collaborators, particularly Peter Reich, who was the leader behind setting up this experiment or these set of experiments that I'm going to talk about today. And we've been close collaborators on this work for over 2 decades. Also, Melissa Pastor, who was a graduate student of ours. I'm going to highlight some of her work. Tally Lee has been a longtime collaborator. And Callie Worm is our field technician, kind of site manager, who has really made this experiment or set of experiments run for a number of years. And I'd also like to acknowledge our funding, which started out from DOE, but for most of the work that I'm going to talk about, the funding has come from a diversity of NSF grants, and I'll touch on that again at the end. So the questions that I want to address today are basically, how do long-term ecosystem responses to elevated CO2 depend on a number of things, including soil resource supply, plant species composition, and climate change. And I'm going to be talking about work that's been conducted at the Cedar Creek Ecosystem Science Reserve in central Minnesota, which is located at the prairie forest border on the Anoka Sand Plain, a glacial outwash plain. And Cedar Creek is also a long-term ecological research site. So the main experiment that I'm going to talk about today is the Biocon Experiment, which stands for biodiversity, CO2, and nitrogen. This experiment was established in 1997, and the main experiment consists of almost 300 2x2 meter plots. And this aerial photo, actually, you can see each of these plots. And this is a full factorial experiment. It consists of a biodiversity treatment where we have 0, 1, 4, 9, or 16 perennial herbaceous species coming from 4 plant functional groups. And you can see the diversity of plots in this photo. These 4 plant functional groups include legumes, non-fixing forbs, or non-end-fixing forbs, C3 grasses, and C4 grasses. And we have 4 species in each of these functional groups, and this pool of species is the species from which the species richness treatments are randomly drawn. Biodiversity is crossed with CO2 manipulation, and we manipulate CO2 using phase technology. So we have 6 20-meter diameter face rings. 3 of them experience ambient CO2, and then 3 are set to receive elevated CO2 at 180 parts per million above ambient. And this is a manipulation that is only during the growing season. And this is just a face-up, a close-up of the valves that feed or that control the CO2 delivery to the pipes that then deliver the CO2 to the plot. This biodiversity and CO2 are crossed with a nitrogen treatment, where plots either receive ambient nitrogen, which is the background deposition is somewhere between 8 to 10 grams of nitrogen per meter squared. And then the nitrogen treated plots receive an additional 4 grams per meter squared per year as ammonium nitrate. Then within the Biocon experiment, we have a second experiment, Terracon, which stands for temperature, rainfall, CO2, and nitrogen. So these 4 treatments are crossed in a fully factorial manner, but they are all imposed on 1 level of diversity, the 9 species treatment. So they're not crossed with diversity, the temperature and rainfall components. Rainfall manipulation was established in 2007 and temperature in 2012. And this just shows a close-up of one of the heated plots. And so we heat the plots above and below ground using a combination of infrared heat lamps and soil heating rods. And so plots either are experiencing ambient temperature or heating to 2.6 degrees centigrade increase in temperature. And we achieve this warming using a feedback control. So the warming level is constant, both above and below ground, throughout the growing season. And then finally, the rainfall treatment is a rainfall reduction, where we put in place temporary rainout shelters. And these are manually put into place during rain events. So there's very little unintended, chamber effect from these rainout shelters. So plots are either experiencing ambient rainfall or about 40% reduction in rainfall events. And again, this is imposed during the growing season only. So all of these plots experience a regular Minnesota winter. So my first question then that I'll address is, how do long-term ecosystem responses to elevated CO2 depend on soil resource supply? And so we might expect interactions between CO2 and other resources because plants require a diversity of resources. And then, indeed, this idea that nitrogen in particular would constrain response to CO2 has been around for a long time. So what have we seen in terms of interactions between CO2 and nitrogen and water? So this graph shows total plant biomass, and the dark shaded bar represents ambient CO2, and the lighter bar represents elevated CO2. And you can see that under the low nitrogen, low rainfall conditions, so this represents ambient nitrogen conditions, and then the reduced rainfall achieved through the rainout shelters, that we see very little response actually of plant biomass to elevated CO2. But if we relax that nitrogen constraint by adding nitrogen, we see an increase in the response of plant biomass to elevated CO2. And similarly, if we relax just the rainfall constraint, so we allow plants to receive ambient rainfall, but maintain this low nitrogen condition, we also see an increased response to elevated CO2. And then if we relax both the nitrogen and water constraints, so the plots are receiving augmented nitrogen and ambient rainfall, which is the higher rainfall condition, we see further increase in response to elevated CO2. So good evidence that both nitrogen and water constrain how plants respond to elevated CO2 in this system. So now I want to talk about how long-term ecosystem responses to elevated CO2 depend on plant species composition. So you'll recall that we have these 4 different functional groups in Biocon, and it stands to reason that these different functional groups might respond differently to elevated CO2 because of differences in things like their photosynthetic physiology, their ability to fix nitrogen, and so on. And so just we have this ability then to compare response of different functional groups to elevated CO2 using the monoculture plots that we have for each of the species. And then we also have a side experiment within the Biocon rings that consists of 4 species plots that contain a single functional group. And so we might hypothesize that legumes, for example, would respond more to elevated CO2 because of their ability to augment soil nitrogen supply by fixation, whereas because of their physiology, C4 grasses might respond the least to elevated CO2. So this figure shows total biomass in ambient CO2, which is the red line, and elevated CO2, which is the blue line, for these 4 different functional groups over nearly 2 decades. And I'm going to focus in today on the C3 and C4 grasses. So we have theoretical predictions about the response of C3 versus C4 grasses based on response to CO2 based on their physiology. And we know that, in many studies, C3 species show an increase in photosynthetic rate with increasing CO2, whereas C4 species tend to have photosynthetic rates saturated at current CO2 levels. And so we might expect these differences in photosynthetic response to CO2 to translate into differences in biomass responses to CO2. So this figure shows, we're kind of just zooming in on those C3 and C4 grasses and looking at total biomass response to elevated CO2. And you can see that during the first 10 to 12 years or so of the experiment, we saw the expected response where the C3 grasses had increased biomass in response to elevated CO2, but the C4 grasses were less responsive in terms of their biomass to elevated CO2. Interestingly, though, we see a reversal happening between 10 and 12 years into the study, where we see that the C3 grasses seem to be less responsive to elevated CO2, and the C4 grasses now are increasing their biomass in response to elevated CO2. So what are some of the factors or the mechanisms that could explain this shift over time in how CO2 is affecting C3 versus C4 grasses? Well, perhaps there is a shift in the effects of CO2 on photosynthesis or on water use efficiency that could explain these dynamics, or perhaps on soil nitrogen supply. So let's consider each of these in turn. So this figure shows data that was first collected by Tally Lee and then Melissa Pastor added more years of data. So we see, so here we're seeing the photosynthesis of C3 and C4 grasses over time in ambient, the closed symbols, and elevated, the open symbols, CO2. And you can see that both of these groups are, how their photosynthesis is stimulated by elevated CO2, but it's a pretty modest stimulation. There's not a huge difference actually between the C3 and C4 grasses. It's in the direction that you'd expect, but it's not a large difference, and it's pretty constant over time. We don't see a shift happening after 10 to 12 years in CO2 effects on photosynthesis between these two functional groups, the way that we see a shift in the biomass response to CO2. This is showing the effects of elevated CO2 on water use efficiency. And you can see that there's a large effect of CO2 on water use efficiency for both of these groups. Again, it's not, both groups are showing a big response, and that response is pretty constant over time. So shifts in CO2 effects on water use efficiency between these two functional groups can't explain the biomass dynamics that we've observed. This graph shows the CO2 effects on biomass compared to the CO2 effects on soil net nitrogen mineralization. And this is a kind of a complicated figure, so I'm gonna walk you through it. So on the x-axis, we have CO2 effect on net nitrogen mineralization. And on the y-axis, we have CO2 effect on biomass. And each of the dots represents the average for either C4 or C3 grasses over a 4-year period. So the closed symbols are the C4 grasses and the open symbols are the C3 grasses. And we have these 4-year periods starting in 1998. And I've numbered them here, and I put the corresponding number onto each of the dots. So for example, these are the average of C3 grasses over the 1998 to 2002 period. And so if you look over time, you can see that the C3 grasses are kind of moving in this direction, where the CO2 effect on biomass is declining, and that seems to correspond to a decline in the CO2 effect on net nitrogen mineralization in plots that are dominated by C3 grasses. On the other hand, the C4 grasses seem to be moving in this direction, where the CO2 effect on biomass is increasing at the same time that the CO2 effect on net nitrogen mineralization rate is increasing in these plots where we either have monocultures or 4-species mixtures of all C4 grasses. So there seems to be something going on, some kind of soil nitrogen feedback where the plots dominated by C4 grasses are showing stimulation of net nitrogen mineralization over time, and the opposite is happening in plots dominated by C3 grasses. Okay, the final thing that I wanted to touch on is how long-term ecosystem responses to elevated CO2 depend on climate factors. We've already talked a little bit about rainfall. We'll talk about that again, as well as talk about warming. So we might expect that warming would have direct effects on plants in terms of their physiology, for example, that might affect their response to elevated CO2. But warming can also affect soil resources by drying out the soil, by stimulating net nitrogen mineralization rates. So warming could affect response to CO2 through effects on soil resources as well. So this graph, this set of graphs shows net primary productivity above and below ground in response to warming here, rainfall, CO2, and nitrogen inputs. And in each case, the dark symbols represent the treatment, and the open symbols represent the ambient conditions. And you can see that all of these factors actually have an effect on net primary productivity. And so warming is increasing NPP, and we've already talked about CO2 and nitrogen a bit. Those are both increasing NPP, and then of course reduced rainfall is decreasing NPP. But we were kind of surprised actually that the warming effects were larger, and for the most part, than the effects of added nitrogen when we think of this system as being so strongly nitrogen limited. And then we see important interactions among these global change factors, both synergistic and antagonistic interactions. So here we have net primary productivity on the y-axis in each of these graphs. This first graph shows ambient temperatures and warming. And then we can see that there's a strong interaction with nitrogen, whereby at ambient temperatures, we see little response to added nitrogen. But under warmed conditions, we see an increase in NPP in response to added nitrogen. Similarly with CO2, we see this interaction that I've talked about before, where we see little response to elevated CO2 or little response to added nitrogen under ambient CO2, but a large response under elevated CO2. We see kind of a different pattern for rainfall, where under ambient CO2, we see that rainfall has a reduced rainfall causes a decline in NPP. But under elevated CO2, there isn't much of a reduction in NPP in response to reduced rainfall. And so that seems to be consistent with that big effect of elevated CO2 on water use efficiency that I talked about earlier. So these water savings effects of elevated CO2 seem to ameliorate the effects of experimental reduction in rainfall. So I'll leave you with some take-home messages from this set of experiments. One is that the long-term responses to interacting factors are not always predicted by theory, so they're not always what we would have expected. So we've been sort of continuously surprised over the course of this experiment. In addition, species composition and functional group composition are a key driver of response to global change factors. So these different functional groups are responding differently, and those differences have changed over time. CO2 and temperature and nitrogen and water are all important in influencing primary productivity in this system that historically we thought of as being strongly nitrogen limited. And so that is consistent. These interactions among all these factors are consistent with multiple resource limitation and also the water savings effects of elevated CO2. And so I'll leave you with just one last sort of comment, and that is that maintaining this set of experiments has required about 10 major grants from NSF. And as I mentioned, it was started with DOE funding over 2 decades. And so that represents a huge amount of work because that's just the grants that were funded. And of course, there were a bunch of grants that we have written that were not funded. And I just bring this up because it highlights the difficulty of funding these long-term multi-factor experiments. And every time that we've submitted a grant to NSF, we kind of had to come up with a new twist on it, which has made it especially challenging. You know, it's not enough to say, oh, well, we've been surprised in the past, and so we expect to be surprised in the future, so you should give us more money to keep this experiment going. So I think that's something that's worth discussing. Thank you.